The following content has been provided by RWTH Aachen University.
Welcome to iOS application development class number 3 today. So today we're going to do two things. We're going to take a look at a couple slightly more advanced topics in the Swift programming language, and we're going to give you a very first glimpse into UIKit, the default API and SDK that you will be developing your interactive apps with. So the default UI toolkit that that you use for building apps. The things that we talked about last time, just as a quick recap here, were mostly about some Swift basics. So you've seen things like let versus var. Remember the differences there. The fact that we have a design pattern, basically a convention in Swift, that using constants a lot is a good thing because it means that things are not mutable. They're not supposed to change. And if that's the case, then you kind of ingrain that into your code by using a let constant instead of a var variable. We also talked about type inference. So it's a very good programming style in Swift to just initialize a value to initialize a variable to some value and let Swift figure out what the type is automatically. That also further removes the appearance of things like uninitialized variables. And that is also something that Swift deals with in optionals. We've seen that there are very good reasons to have variables that may not have a useful value yet. And if that is the case, there is a specific construct, again, that Swift enforces you to use if you want nil to be a valid option for the values of your variables. If you do, then nil is okay. But remember that once you do that, these are no longer type compatible directly with normal variables, simply to keep you from possibly running into a runtime situation where you are assigning nil to a regular variable and then try to do stuff with it, like printing it or stuff like that. All right, we also talked about tuples, which are a neat extension of Swift that just makes your code more compact and easier to read by just using tuples on the left-hand side of assignments. That's an unusual setup for programming languages. We talked about more things there. One thing that I think we didn't actually mention, it's a small detail, but you might stumble across this if you come from Java, C, Objective-C, and so on. We talked about statements like if, else, etc. And with these in Swift, you always need curly braces around your statements after the conditions, right? Even if it's only one statement. C used to be a little lax about that. It let you put a single statement after an if clause without putting curly braces around it. And that, of course, once you extend then your code, you refactor, you add a second statement. It's a wonderful space to make things that go horribly wrong and really hard to discover bugs. Another reason why Swift is trying to keep you from making those mistakes. So there's always going to be curly braces around the statements after things like if, else, etc. Then Phil went on and covered a couple IDE basics. We talked briefly about the fact that you can run Swift in the terminal. It's one of the longest booting or longest loading apps that you can launch on your command line that still actually has command line interface. It takes a long time, but it's super useful. And alternatively, Swift Playgrounds, you can download a dedicated app for that. Even on the Mac, also on your iPad, by the way, you can run Swift Playgrounds on the iPad. You can't run Xcode on the iPad, but Swift Playgrounds works there. So if you have an iPad, you can actually dabble in Xcode really nicely and try out some small things, while you're out and about. And then, of course, there's Xcode, the sort of, the king's way of doing things that can do everything and the kitchen sink. Within Xcode, then Phil gave you a couple ideas about how the project settings work, how the simulator runs, and how for many things you actually won't need an iOS device around to test them because the simulator is actually pretty good. And there's also the interesting way how the IDE supports a fairly usable and easy to use way to link code and interface. It's always a struggle of IDEs how to make those two sides of the equation be meshed together. And IB outlets and IB actions and the graphical way to actually connect those is a really nifty way to do that, especially if you're only doing a few of those. All right, so now on with Swift. First thing we're going to talk about is strings. This is not too exciting. Strings are just collections of characters. They're not like C strings. This is important to remember, and will give you a medium amount of grief as you dabble with Swift and then try to use more low-level APIs that actually do use C convention characters, with a trailing 0 or those kinds of things. So Swift is different here. In Swift, these are character collections in Unicode, so they can contain Unicode characters. It's not a problem. And they have things like .count will tell you the length of a string, for example. This also already hints at the fact that strings are not your very basic simple data type with nothing attached to it. It's more a bit like in Java where strings are a class. Here strings also apparently seem to be something slightly more complex. They could be a struct, they could be a class, we don't know yet, but we see that with the dot operation, obviously strings have methods attached to them and other member variables attached to them than just the pure contents that they contain. Now, individual characters are somewhat of a specialty in Swift. Usually in C-like languages, you would expect to be able to have your separate character char data type and be able to define literals in that with like just single quotes, right? Single quote A, single quote is typically your byte/character back in the ASCII days. But Swift does away with that mostly. If you just define a single character, you cannot actually use single quotes in Swift. It doesn't exist to define literals. But if you want a single character string to actually be of type character and not of type string, you need to tell Swift, right? So you see the first line down there defines letter 1, and that's a string variable because that's how Swift type infers this. Letter 2, we told it that we want this to be of type character, and we initialize it to a single letter string, which is possible. A single Unicode symbol, I should probably say, to be precise. So this is a little weird, maybe. Other things are very normal that you're used to. So for example, if you want to check whether your string is empty, you can actually call the isEmpty compound here. So this will tell you whether it's empty or not. You can just ask for that. Note this is not a member function with round parentheses around it, but you call on that just like you would call on a member of a struct, for example. Then how do you concatenate strings? That's pretty easy. The plus operator is overloaded for strings to do that for you, and it does the usual things you would expect, right? So two strings here, S1 and S2, you can join those by using the plus operator. And then if you can also do that with string literals, for example, here as we do for S4 here. And note that we defined S4 as a var instead of a let constant, because next line changes it. And so here you can also see the plus equals shorthand that you know from other languages like C and Java still works here as well. Basically just expands into S4 equals S4 plus greetings. Below that, you see something that we already hinted at in our slides yesterday, sorry. You can see that we can insert the values of expressions into print statement strings by simply using this backslash and round parentheses. So you're going to see that a lot as you use, especially if you use either the console for output as you do in the beginning before you're writing graphical apps, or if you are doing string manipulation as part of your application, right? So whenever that's the case and you need to insert something into a Swift string, you use this backslash round parentheses notation to add non-string parts to your string. This also then takes care of finding the sort of printable version of that value. So for example, A and B are here integer variables or constants, sorry, and the int type automatically has a way to convert itself into something that can be part of a string. Next up with strings, you always want to know, how do I compare them? This is also, depending on which language you're picking up, this can be slightly different. Here we have an example with month being August, other month also being August. And as you can see, even though obviously these are, if you think about it, two different constants, so they're not the exact same thing in memory, right? They've been put on at different spaces in memory, but they still compare with the double equals comparator to be the same. So Swift takes care of that for you. It doesn't force you to go through and call a clunky equals function on strings. The equal operator turns out to make things equal if they have the same contents. Lowercase and uppercase, however, of course, differ, as you would expect. So you can see then the next line there, this second one would also trigger, because month is not the same as lowercase month because it's spelled with lowercase a. If you want to find out whether the lowercase version of a string is the same as the lowercase version of another one, you can just do that by calling the lowercase member method of the string type. And here you notice there are round parentheses around it. So we've got a name here, and then if we call name.lowercase parentheses, that returns another string which contains the original one in all lowercase. And then, of course, no matter how you capitalize the thing that goes in, lowercase will give you the lowercase version out, and so they compare as equal. So far, so good. This is easy stuff. Now, functions. Things get a little funkier with functions, I would say. But first of all, it's actually, it might look pretty normal. There's only a bit of syntactical sugar that is a little different than what you might be used to. So the general way to declare a function is with a func keyword. Then you say what the name of the function is. Yeah, I know, it's func. You specify the parameters in round parentheses, nothing surprising here. And then comes the right arrow made up of a minus sign and a greater than sign. And that defines the return type, if there is one, if you are returning anything. Okay, that's maybe a little unusual. Then you've got the body of the function in curly braces, as you would expect. Down there in the bottom here of the slide, you see this very simplest example where we don't have a return type, we don't have any parameters. We just define a function to display the constant pi, and that's simply done by the way that you see it there. And you can call it just by calling its name with the round parentheses around it to indicate that you're calling the function. Now, next up in complexity, of course, is if you add a parameter. If we only have one parameter, it looks like what we've got at the top there. And there's a couple of things that I want to point out here that are unique about Swift and that let you get a taste of how Swift expects you to write things. First of all, what you'll notice here is we're specifying the value, and then there's a colon. Value is the name of the parameter, and behind the colon is the data type of that parameter, right? Obviously. That's not surprising, right? But what might be surprising is when we call this function with that single parameter, we're actually mentioning the name of the parameter again. And that's something you're probably not used to from things like Java. The reason for that is, and that's why I put this little logo behind it, is this is a way that Swift enforces or encourages ways to write code that is more readable on the side of the caller. So when you are calling a function, Swift is trying to make that code that you have to write to call a function as readable as possible. So this is why we're seeing this. Now you might say, that's unnecessary. Why do I need to type value there? Well, first of all, you don't really need to type it out because Xcode has excellent autocomplete functionality. So you will quickly find that you hardly ever type these things out in full. You just start entering print triple, and then it will give you a complete template for that thing. And with tab, you can easily jump to the various things you need to fill in, and you normally don't need to type these things. But they are there once the code is written for somebody else or yourself, 3 weeks from now when you don't remember what you did there, to read your code and find your way around it. And the other reason why this is handy is especially if you have more than one parameter. So if you look at the lower part of the screen here, that slide, I've got a function there that prints out the, it's a power function that prints out its result. So it's not returning anything yet, but it takes two arguments, a base and an exponent, okay? And let's say the base is double and the exponent is an integer, and what you return is basically nothing, because you just compute the result and then you print it out. But note, and this is the important part here, how you now read the lower way, where the lower part where this function is called. Print power base 2 exponent 3. This is super readable, right? Now, if we didn't have these tags down here, these labels that tell us what these parameters are, then yes, it would be a little more compact to write or to read. It would take less space, but that's not a concern in Swift. What we really get here is that we know which parameter means what. And if you've ever had parameter calls with like 6 or 8 parameters in there without any labels, you always have to go back to the definition of the function, right? And look and basically do some pattern matching yourself and figure out, okay, is the third parameter the IP address or the fourth one? And which of these trues and false belongs to which of these many parameters in this function? It's a mess, right? Reading this code is usually really hard, and Swift makes that much easier. So your code will be longer to look at, but actually it's more readable that way. And the idea that Swift tries to enforce it, that your code should almost be understandable if you just read it out aloud. This is an important principle, and we're actually going to do one on top of that. We're going to do you one better with this to make your code even more readable. And this is using argument labels, because Swift gives you not only one way to give your parameters a name, but actually lets you give them 2 different names. The reason for that is that oftentimes the name for a parameter is not, the name that you use inside a function so that your code reads well inside that function is often not the same word that you would use to make the calling of that function highly readable. Here's an example. This function says hello to 2 people, right? It prints out hello person and another person. Now, this reads well inside the code of the function, right? Print hello person and another person. But if you call this function, if you were to call it with these same names, then we'd have to say hello person colon Mike or Miles, another person Riley. It's okay, it's readable, but it's not nice, is it? It's not how you would say it. You would say hello to Miles and Riley. That's how you would say this, in everyday language. And that's exactly what you can do with Swift. Because Swift lets you give another label, it's called an argument label, to your parameter. And that argument label is something that you will actually only use when calling that function. It's not used inside the function body. There you use the parameter name, like person, for example. But when somebody calls that function, they can use the argument label instead. And this means that you can actually do the call that you see below here, say hello to Miles and Riley. Now, isn't that nice? That's really highly readable code. And at the same time, you don't need to use to and as internal names of those parameters, because that would look horrible, right? Print hello to and that's not readable code. So you see there's 2 different ways, 2 different points in which these names are used, and they have a different semantics. And so the challenge for you as a good Swift coder is to think about what's the best term to call this parameter inside my function, and what's the best term to use when I call this function for others, when me or others are calling this function, what's the best word to use in that context? And this is a good example of how you would design that so that both of these parts read highly naturally. The lower part here, again, of this slide shows you another option that you have, because sometimes maybe you don't want to use a named parameter in the call at all. And this you can do by specifying a special kind of argument label, which is the underscore. If you use the underscore, that means to Swift that you can actually call this function and provide the value of this parameter without giving any label to it. Neither the name that the function itself uses internally, nor the argument label instead. So that's, in this case, you could shrink this down to say hello, Luke, Dave. When would you use this? Well, when it is 120% clear what your parameters mean or what your single parameter means, and you're not concerned with this, right? So open URL and then comes a string, and then everybody knows that's the URL. It doesn't make sense to call this, open URL and then URL colon, right? So you could drop that, and then everybody understands from the context what you're doing. But use it sparingly. Only use this when you really think this is the best way to write your function, and you really don't need that explanatory label or original parameter name there. By the way, this is in part inherited from Objective-C, if you've ever seen that around. Objective-C was also a language that was encouraging people to write more verbose code with great autocompletion that was easier to read. And Objective-C always left the first parameter unnamed. So there you would say like open, and then your first parameter might be URL, and then the second one might be with encoding or with whatever. And so it's kind of Swift is inheriting from that. With Swift, you can do the first parameter without having a name, like in Objective-C style, by using the underscore. Right. Now, default parameter values are not that exciting. You simply specify a default value with this equal 0 here, for example, for that second parameter. So we've got a function display team name score, and that outputs the team name and the score. And if I call this with a normal score, as you would expect, it does exactly what you think. But you can actually drop off this second parameter, omit it from your call, and then it will use the default value. Nothing too exciting here. Return values also are not super exciting. We already said that you specify them in your function declaration by using this right arrow and then the type of your return value. And then you just use the return statement that you know from C and Java. And you can see here, you would then call this, you can use this then as a right-hand value that you can assign to a variable, for example. Nothing exciting. One thing that is weird, you're not seeing this here, but you will see this often, for example, in SwiftUI. In Swift, unlike other languages, you can actually use an expression as a statement. So you can actually drop the word return here in this line and just say result. And that would look weird to most people who are used to more conventional programming languages, but an expression by itself, if it returns something, can actually be a statement by itself. So in SwiftUI, this is often used where the return is not given, but instead it's just the expression, and the expression itself then becomes the return value. But we'll get back to this, I think, when we look at SwiftUI. All right, that's functions. A bit weird, but not too weird. Now comes maybe possibly the most important thought change in Swift that you need to wrap your head around, and that's structs. The Swift language and the SDK, UIKit, but also SwiftUI, really expect you to use structs until you really, really need a class. Okay, so you may have gotten used to Java using classes for pretty much everything that is beyond a single, basic type like integer. In Swift, it's different. You often end up using structs. The reason for this is performance, because the designers of Swift found that in modern systems, oftentimes when we work with classes, which inherently means we've got objects somewhere out there in the heap, right, that we point to using our object pointers, which are basically our object variables. And multiple objects can point to the same object in multiple object pointers, or variables can point to the same object in space. This whole thing that classes do has a lot of overhead associated with it. It turns out that oftentimes, rather than having an object in the heap and changing something inside it without destroying it is actually more expensive than just throwing away this whole data structure and building it from scratch. And this is what structs do, because structs don't end up in the heap. They end up on the stack. They're basically just like ordinary variables or data types. So most basic types in Swift are actually structs. So they are what you would call a value type versus a reference type, which you have with classes. So as you know, if you pass a class object onto in a parameter, you're really giving the caller a pointer to that data structure somewhere on the heap, and it'll mess around with it. Whereas in Swift, you're often passing structs, so you're passing that whole chunk, just gets straight piped out to that function that needs it, and it can do with it whatever it wants, because that's a copy, right? This is not the same piece of data that you had in your calling code. This is something you will run into many times as you're coding in Swift, whether it's in UIKit or Swift UI, and you really need to wrap your head around this. So first of all, string, int, double, bool, they are all structs, and that's why we were able to use things like a method on a string, like string.lowercase, right? The most basic way to specify a struct is simply with a struct keyword, and here I have a custom struct that I call person. Notice that we're using an uppercase P here, just like with classes, to distinguish variable names that identify or struct type names from initial from simple variables or constants. So person is a struct, not a class, but it's actually in many ways similar to that, except for that fundamental difference, value type versus reference type. And that struct has a single member here, which is a name. It's a variable name, so it can be changed, and it's of type string. So I could specify a new struct with a let constant here, which means that struct will actually be immutable. I can change it later on, and I generate it by calling the the initializer the way that you would expect it from Swift. And as you can see here already, we can specify the value that should go into that member variable name with a string literal Jasmine. If I then run print first person.name, it'll output the name of that string variable. So there's a couple things going on here. For example, we can already see that structs can have methods. We can also see that we create these structs similarly how we create objects in Java by calling the initializer, which is represented by this name of the struct, person in this case. So structs can have methods, right? So here's an example. If we add to the person struct this function, say hello, then it can just refer to the member variable name directly, as you would expect from Java, for example. So nothing too exciting here. This basically person.sayHello then calls this, and it outputs it. So what you've noticed with this, and also the last slide, is that we've created the person by giving a value for the name, right? So this has to happen somewhere. We have to give that name a value because it's not an optional. It can't be nil. And so we get to the point of initializers. The simplest way to use an initializer is just to have a variable and equal it to the struct type dot init, right? Calling that init function explicitly. You could do this for string, integer, or Boolean, and those would give you basically readily initialized strings, integers, or Booleans with those default values that you see to the right here. But nobody writes this in Swift. Everybody uses the shorthand, which is just writing the name of the type of the struct type, string, int, or bool in this case, and the round parentheses right behind that. Right? So this is what you'll see all the time. Notice that technically we're not telling Swift what type it should be. We're not giving it a colon type declaration here, but because it's assigned a value that is basically an initialized string struct, we know that this variable string will also be of that type. Now, again, defaults are easy to do. If you have to write your own custom struct and you have a member variable in there that you want a default value for, if the user doesn't specify anything when initializing a new type of the struct, then you can do that, right? By just providing this equals 0 here in this case. And then I have two options, right? I can just literally just create a new struct of this type odometer with a default value. This is exactly how the built-in structs like string and bool also do it, right? Or I can specify the parameter as before with the example of the name equals Jasmine. Then we get the custom value that we want. Talking about initializers, so far we haven't actually written an initializer, right? We haven't actually, it's always been synthesized and generated for us. You can write your own though. Here's an example where you might want to do this. We may have a temperature struct, and that could contain its value that we call Celsius, but it might also include two different ways to initialize it. One would be the standard one. If I provide a Celsius value, then it will just associate the value that I pass in as a parameter into the initializer with the value, with the member variable Celsius itself. That's how you would expect it. And that, if that was all you wanted to do, you wouldn't have to write this, because this is what Swift can do for you. But if you want a custom initializer that instead initializes with a Fahrenheit value and then takes the value, converts it appropriately, and then associates it or puts it into the Celsius member variable, then you need to write that, need to spell that out. And so here you can see how you use these. Down there, we've got one variable that's current temperature that we then initialize to be a temperature struct with the Celsius value set to 18.5, and that would basically call the top initializer, versus the other one here, in this case, a let constant. We initialize to with the Fahrenheit initializer here, so that basically does the little computation and then puts it into the Celsius variable. Note we still only have one member variable, the Celsius type here, the Celsius double, but we have two initializers with different names. And why would we pick var or let? This is not, you can't see that directly from this code here so far, but we have plans with the current temperature to change it later. That's why we used var here in this code. Let is not something we're going to change anymore in this example, so it's a constant. Now, what are we changing? Well, here's the next line of this code. After creating this variable of type temperature, we can then go in and change it, its member variable .Celsius to be something else. So here we change the temperature by changing the property. This is often called, these member variables are often called properties, by changing it directly. And now comes another stumbling block that you are bound to run into, because this is unusual and it's not what you're used to from Swift. And Phil's already smiling. He's like, yeah, been there, done that. You might think, because we just changed a member variable from outside, right? And that was easy enough. You might think, well, that's certainly also possible from inside, wouldn't it? Well, it's not. If you have a struct and you have a method as part of that struct, by default, these methods cannot change properties of that same struct. So my temperature struct here with the Celsius member variable and these two initializers, if I add a member function to it, change Celsius to a new value, you might think that should work, right? I just changed the variable. That's the whole point of encapsulating data and functions, right? So they can work on that data without doing this from the outside. Well, yes, but no. By default, Swift will assume that your member functions only have read access to your member variables. And again, this is put in place for you to be very clear about what you need. So as long as you don't explicitly need a function to be able to change member variables, it can't. If you need this, you need to tell Swift explicitly. So this code would not compile. What do you need to do? Well, Swift makes you jump through a tiny little hoop so that you only do this when you really need it. it requires you to put the keyword mutating in front of that function, right? And that sounds close enough to zombies that it's scary, and you only use it when you really, really need it, right? So this means that you and anybody else looking at your code can immediately see which functions will actually mess with the content of the struct and which ones won't. Because only mutating functions will actually have the ability to change member variables from inside. So this adding mutating in front of this function keyword here allows you to actually change properties. Okay, so however, if we do this, we still need to, you might say, well, we're changing that member variable, but we're not really changing the struct, right? That struct exists. So by flipping that member variable inside the struct, we're not really changing the struct where that is as a whole. It's not a new object, right? Well, as soon as you change a member variable, you actually also need to specify that whole struct that you created as a variable, because you're changing it. And remember, we're doing pass by value. So this is actually done by just throwing away the old one and copying a new one that has the changed value. So talking about properties, you might find that your temperature class, sorry, not class, your temperature struct, see, I fall for this myself sometimes. Your temperature struct actually might need to return a couple different values. So, if you were like, a 7th grader and you were writing that code, you would then put a Celsius member variable in there and a Fahrenheit member variable in there and a Kelvin member variable in there, and let people, and if people changed one, you would make a lot of, da-di-da to change these 3 values and to keep them all in sync. But of course, that's messy, right? That's not what you want. So instead, what you can have is something in between member functions and just plain old member variables. And these are computed properties. Computed properties, they start out like a member variable, but then actually follows the body of a function. And what that means is that you can handle it, use it just like a normal property from calling code, but internally, it doesn't have any state. Every time it's requested, it computes its own value right there and then. And that, by the way, is exactly how the earlier count worked. You may have gotten confused when I said, we can do .count on a string variable, and it'll return the value. You're like, well, what are you doing there? Is there a member variable that contains the count, and every time I change the string, the count gets miraculously updated? Or is it a function, but you're not giving me parentheses after calling it? So what's going on? This was exactly an example of a computed property, right? So maybe go back to that slide when you review this and look at how that works there. So here we have Fahrenheit and Kelvin being computed properties, right? So what you can now do is you can create a new temperature struct, initialize it with, let's say, the default initializer. Note that in this example here, we have no initializers given at all. So this is the way that you can initialize it, because that initializer is automatically synthesized for you from Swift, right? You don't need to write any initializers if all you want to do is this. And then we can actually call things like current temperature dot Fahrenheit. Note no round parentheses around this after Fahrenheit or Kelvin here. We're just accessing these things as if they were member variables or normal properties like Celsius, but they're actually computed on the spot at this moment. But wait, it gets better. If you have these kinds of properties, you can also actually watch for when they change, or even when they are about to change. And this is really neat. This is something you often need, especially when you write, user interface code, event-driven logic, where you need to figure out exactly when stuff in a model class changes, or a model struct in this case changes, and you need to update your user interface. This is how you can hook in. So you can have, let's say we have a struct that's called step counter, and it has a property called total steps that is of type int, and we initialize it to 0 by default unless the user tells us something else. We don't write any initializer, any custom initializer, so the standard one gets synthesized for us. And note that behind this normal property here now comes not normal code like in the computed property, which had the return statement to tell you what to say what's going to be returned, but instead it has these special will set and did set sections, right? So will set is a piece of code that says execute this code right before the value of this property is changed. And similarly, did set will get executed right after this property is changed every time, automatically. Super useful, right? So if you create a variable of that type and then set the total steps to something new from its default 0, then actually it will execute both the will set and the did set. And even if you then change the value to something else, it will also then again execute all of these two, right? Both the one before and the one after.
Okay, so now that Jan has talked about the structs, I will go into a little bit more detail about the other big structure that you can use, which is classes. And classes are very similar then to the classes you're aware of from other programming languages. And compared to structs, one of the big differences that classes are reference types. So while if you copy a struct around, it always creates another copy. And if you change one instance, it doesn't automatically affect another instance. This is then true for classes. So those are more passing pointers around. So if you change something, then it will affect this whole object that you created from a class. And the construction of a class is very similar to also that you were shown now for structs. You start just instead with the class keyword, and then essentially everything stays the same so far. So you can have your member variables. So here, for example, if we have a class person, then this person has a name, which is of type string. And you can write your initializers. So here the name is passed over in the init method and then assigned to the member variable. And this is also something that is quite interesting to know. So this name was a constant or is a constant. So we have let name, but we don't assign automatically something to it. This is fine. But then you need to assign it as soon as possible. For example, in the initializer, that you then specify self name and assign a name to it. Otherwise, the compiler will already complain that you have something that is not initialized. And then similar for functions, you can have your function that just says hello and then just prints out hello there to the console. So the example here, if we create then a person with the name Jasmine and print out the person name, that will access the member variable and just printing out Jasmine. Or we can call the function say hello, and that will just print hello there then to the console. So that classes are reference type is one big difference to structs. And the other big difference is that you can have subclasses of classes. So here we have a class student. We just show or have a colon and then the class person behind it that signals that the student is inheriting from person. So it takes all the member variables and all the functions from the original person class. And here we assign a new variable, favorite subject of the student, and that is also then a string. We can also create then a new initializer that not just takes a name, but also the favorite subject. And within that initializer, we then assign this new favorite subject also to our favorite subject member variable of the student. But we don't necessarily need also to assign the name ourselves, or if you have multiple member variables already in the base class, that then would be a hassle to having to set everything yourself. So you simply then call the init method of your superclass by calling super.init and passing over then the name there. So that will set up the name property in your student as well. And for the if you have functions that you want to adapt or change. So for example, our person class already had a function say hello that just said hello there. If our student wants to say something different, say hello is called, then you need to add this keyword override. That makes clear that this is a function that already exists in your base class, but is now adjusting that that function. So here, instead of printing out hello there, we print out hello student. And we can do that because we said that this is overriding the already existing function from our base class. And so that is essentially the difference between structs and classes. So with only one slide, we've now also introduced classes, what is happening. And that is enough for now that you know. So for classes and structs, just keep aware classes are reference types, and there you can have an inheritance. And it's something that Swift also recommends that you do, starting out with structs so far as you come, and then if you really require the additional features of classes or subclassing, then switch over to classes. It's just not very difficult to change it also along the way. And with that, we move over to collections that allow you to group certain objects together. And you're already aware probably of a couple of those. So the most common collection types are all also included in Swift. And two that are very frequent are arrays and dictionaries. And they're all created also very, very similar. So for example, for an array, you have your variable name, and then you indicate that it is an array by using these square brackets. So if we have square brackets, string, and closing square bracket, that is an array that has only the object types of string in there. And you can also do that, assign values to that by having square brackets and then a set of strings. That is also fine. So with type inference, we don't really have to explicitly mention here the square bracket string after the colon. That will be inferred or would be inferred by the compiler as well. And dictionaries are just keys associated with different values. So here we have a dictionary of scores, where we have Richard, Luke, and Cheryl as our keys, and the integer values are associated with the corresponding keys. So Richard has a score of 500, Luke of 400, and Cheryl of 800. And here we don't really also specify the type explicitly. The compiler infers that for us. And this is also something very important to keep in mind, that in Swift, collections are value types. So it's different from a couple of other programming languages where you're used to, okay, I'm passing an array to a function, I'm changing something within that function, and that will also automatically change the array that I have outside of the function. That is not the case in Swift. In Swift, if you pass over an array, that is a copy of that. So all the changes you do within that function are not automatically applied to the array outside of the function. So in practice, you often don't really notice that because in the background, Swift optimizes also the storage. So if nothing changes, it's not copying stuff around. But if you change something, then there are the changes. And something that you will see quite often is that if you have a function that is changing something in an array, it will also return then that change. And usually you then assign this directly again to the array that you want to adapt. And that is also possible because functions can return multiple things, for example, in tuples that you have multiple returns in there. So let's look a little bit closer into arrays and how you can construct them. And there are a couple of different ways. They all essentially do the same things. So for example, if you explicitly mention that you have an array here of integers in the first line, and you assign it an empty array by just having empty square brackets, that creates a empty array that just takes integer values. And the second line essentially does the same, where you have an array in the, how is that called in English? I'm not sure. Pointy brackets, something like that, maybe, and have the type in between. That is something that's just mentioning, okay, this is an array, and the type that the array will have is also of integer. So it's a different way how you can specify the type of this array. Or you can also just have the integer and then the normal brackets that call the initializer and assign this to your variable, and then the compiler will also automatically infer, this is an integer array. So there are a number of different ways how you can initialize your arrays, and don't really change anything whether you use one or the other. And the option that you have for the bracket version, that is essentially calling the standard initializer, but you can also have different, or the array type has different initializers. So for example, I can say already fill the array with default values or values that I want by calling repeating count as the function. And so this will now create an array that has 100 spaces, and all are set to 0 directly initially. If I want to access values, that is just taking the variable name and then having in square brackets the index that I want to access. So starting, of course, at 0, taking index 0 will give me the first element of the array. I can also access it with a function just calling first on the array that will also give me the first input there. And similar to other functions, if I want to set a different value or change it, I assign a new value to that location. So for my array and 1, I can assign then a new value to that. So instead of 0, it now has the value 2. And if it's a variable, that is possible. If it's you initialize your array as a constant, then you can't change the values that are included in that array. I can also append or call the append function and just add a new value to my array. And of course, there are many different functions and things I can do with arrays. So this is just a very brief overview of that. Now for dictionaries, it's quite similar. So there are, again, a lot of different ways how you can initialize your dictionary. And for that, you need to specify the type of the keys that you're using and the type of the object that is associated with the keys. So here in the first line, you again have square brackets, but then you have first your type of the key that you're using, and then a colon and the type of the object that you're using. And the only requirement for the keys is that they are hashable. So that is a protocol that the objects need to implement. Strings work, integers work. So there are a lot of different keys, and you can also write your own classes that apply to this protocol, and then you can also use them as keys. And similar to the arrays, you could also specify the type using the pointy brackets. They're just separated by a comma, your different objects that you're using. So for creating a dictionary, you can also directly create it and fill it with values. So here we have again our scores that have a string as a key and integer as the object that are associated with that. And the compiler then will already infer that it's a string for keys and integers for your values. And if I want to add a new key and assign a new value to that, I'm just setting or calling the scores with a new key in our square brackets and assign then a new value to that. So in the second line here in our examples, we're creating a new key Oliver and assigning the score 399 to that key. And the next line, yes, combining already a couple of things. So first, we're calling on the right-hand side, we're calling the function update value. And the first parameter that this function takes is the new value that we want to put in. And then we need to specify for which key do we want to do that. So calling scores update value 100 for key Richard will adjust the value of our key Richard here, setting that to 100. But what it also does, it returns the original value that was in there. So on the left-hand side, we assign a new constant with the old value, and that old value will have the value 500, because before we updated the value, Richard was associated with the score 500. Something that isn't directly apparent here is that old value is then not an integer. It is an optional integer, because the key that we want to update it for might not exist. So in that case, it wouldn't return or couldn't return an old value and would have to return nil. So automatically old value is set to an optional integer. And next class, next Monday, we'll get then finally way more into detail about optionals and how to handle them. So then what dictionaries also give you easy access to the number of keys or the keys that you're having of the values that are associated in the dictionary by certain members, so that I can access scores.keys will give me all the different keys that are in there. They return an array that we here just explicitly also cast to. And similarly, we can also access all the values that are incorporated in that in our dictionary by using scores.values, returning all the values that are currently stored in there. And the last 3 lines here already show you how you could use or access a value that you want to take out. As we mentioned, if we just access scores, in this case Luke, Luke might not be a key that exists in the dictionary. So again, this would be an optional, and we wouldn't be able to directly add something to that score that is returned because it might be nil, and then you can't combine it with another integer, for example. So what happens in this line is that we assign the return value of if we access scores with Luke, assign this to a new constant myScore, and the if in front of that just means we're checking if that is possible. If it was possible to assign the score to the new constant myScore, and that is actually then also the integer that was in there. So if that's possible, and we have scores Luke returning an integer, then we can print it out directly. myScore is of type integer and not of type optional int. So then we can print it out directly and have the 400, or be able to adjust the properties that we want, compute new scores, for example. So that also, yeah, brief overview and easy, quite quick taste into how to handle optionals. And like I said, next week we'll get way more into detail how you can handle those. But another important thing that you're doing with programming language is iterating. So, and Swift is quite easy there with for loops, because the for loops are quite powerful and offer already a lot of options how you can yeah, choose how often to iterate and how to access different information. So quite the standard setup is that we specify here we want to iterate over the numbers 1 to 5, and so we just write for an index and then the keyword in, specifying that you have a range, specifying the range with the dot value that we already saw for the ranges in cases, switch case constructs, and then having curly brackets the actions that we want to do. So here, then we have within our for loop also access to the variable index, which takes the values from 1 to 5. And in this case, it's including also 5, so that it also takes the ends into account. So if we just want to iterate a couple of times over or a certain number of times and want to repeat something there, and we are not really interested, we don't really need the index, similar to the functions that we spoke about. If you just have an underscore, yeah, you don't really assign it the iteration to a new value. You just iterate here 3 times and printing out hello for 3 times, but you don't have access to a variable index over the time. And with for loops, it's also quite easy to iterate over arrays. You simply specify a new variable that you want to use as your iterating variable, and specify then, okay, I want, in this example, I have an array of names that has 3 names in that. And by specifying for name in this array names, I'm iterating over all the objects that are in that array and get them one by one, and I can print out these different names. And that is also possible directly with strings, for example. If I iterate over a string with the same syntax, I'm getting every letter in sequence. So here it would print out each letter individually directly by just using this for loop. And if I'm not only interested in the elements of the array, but also at which index they take place, then I can do that as well by having a tuple as my in iteration variable here with index and letter. And I'm not only iterating over an array, but I'm creating a new array by enumerating the elements of the string here. So having the string ABCD and enumerated gives me a enumerated array of these different letters. So now I'm if I'm iterating over that, can print out the index where the letter is taking place and the letter at that position. So this will print out 1A, 2B, 3C, and so on. And of course, it also works with dictionaries. That if I have here a dictionary with vehicles and they have yeah, a string as the key, and then the number of wheels that this vehicle has as the value, I can similarly iterate over this dictionary, that I create a tuple that has the name and the wheel count directly in there. So for each element in my dictionary, the key will be assigned to the variable vehicle name, and the value will be assigned to the wheel count. So I can then print that out directly with this for loop. And it's something that, yeah, is something, play around with that, see what is possible, what different structures can you use there to iterate over your collections or over your ranges, to get a feel of, yeah, what works and what doesn't. But yeah, for loops are not the only ways how you can loop through different actions. While is of course also possible to have a while loop, and the syntax is there again quite similar to other programming language, that you have the keyword while and then the condition that is checked whether it's true or not. And if it's true, then the action behind it is carried out. So here, printing out the number of lives that are left, and then in this case, you need to should adjust the number of lives so that at some point it gets to 0, and then the condition is no longer true, and the loop is not repeated anymore. And the two examples there on the bottom is yeah, just another way how you can control that, that you have while checking the state of a Boolean, here create a Boolean still alive that is either true or false. And while that is true, while we are still alive, then something should happen. In this case, we're just reducing the number of lives. And if then we are at 0, we adjust the still alive to be false on the left-hand side, and then we'll stop this iteration. But we could also use the keyword break that would break out of this while loop and continue with the executing the code afterwards. And yes, there are also more ways for iteration, but for loops and while loops already are a good starting point, and you will see the other ones when you need those. So that is it for the Swift portion of this week's lecture. Now I want to just give a brief overview also of a UIKit, because UIKit is yeah, essential for every application you're writing for iOS. And UIKit provides a lot of the visual elements that you're seeing in your interface and that you can use to display data, to allow the user to control the app, and so on. And so I will briefly give an overview of UIKit. And for UIKit, UI view is the starting point for everything visual that you see on your screen. So all the different elements that we, for example, also saw yesterday, like UI label, UI button, they are all subclasses of UI view. And there are quite a number of views that come directly for storyboards, for the interface builder, that you can directly use to lay out your app. And just want to give you a couple of examples that we have. So labels are just simple for specifying text. If you need more control or you have a longer text view, UI text view is also then very often needed. And you will see already that the UIKit elements and the UI view subclasses, they also start with UI, makes it easy to know directly, okay, this is something that is related to UIKit, that is related to UI view, and it gives you already an impression of what you will be able to do and what behavior you can expect. For displaying images, can use UI image view. Has already a couple of properties that allow you to control the aspect ratio and whether it should be scrolled, scaled, and so on. For UI scroll view, that allows to display or include more content that would fit on the screen, and it will automatically create the scroll bars to indicate how much space is left, and already conform to the touches that you can pan around, that you can scroll around. UI table view enables you to display a lot of content in a table, and already controls the display for that you don't have to draw all these different cells yourself, but gives you easy access to those visualizations, and also makes it simple to create different sections that are then visually split and are corresponding to the view that you are used to on an iPhone. That it is consistent across all the apps on the platform. UI toolbar for example, sharing items, that you have a place where you can have those actions and include those. The UI tab bar, which is usually then on the bottom, and switching between different view controllers, is also a view subclass that I can adjust. And the navigation bar is used if you have, for example, in many productivity apps, that you drill down into, go into way more detail, then the navigation bar automatically gives you the option to easily go back and display the titles. But so far, these things are mostly about displaying data and showing different elements, but also the various controls that you have are also subclasses of UI view. So you have the button that can take a lot of different forms, with either it's a text button or just a symbol that you interact with. Or UI slider, which allows you to specify a value on a range of values that you can specify. And all these subclasses then have specific information that you can access. Here, for example, the value that you set, and will automatically, if you set it by code, that it also represents that then in the view slider that you have in your interface. UI switch for Boolean terms, whether it's in on state or an off state. UI text view to input or text field to have different text input areas. Segmented controls for a set of different elements that you can be in here. So for example, this is something filtering the probably app costs or earnings that you have, whether it's a paid app list on your free apps or your top grossing apps. But there are also more complex controls like the UI date picker that you can use directly. It's not used by the default apps from Apple anymore, but you can still use this visualization where the user is scrolling through the different dates and setting different times. So these controls already give you a very good set to start from if you want to interact with or want to allow the user to interact with your app. But in many cases, you want to allow for more. And for that, you already have gesture recognizers that therefore basic touch gestures. There already exists some in the interface builder that you can simply drag onto your interface and interact similar to the other controls. So for example, with a tap gesture recognizer, if I add this to my interface, I can connect it with an action, IB action, to my code, and then react once the gesture recognizer recognized that, okay, it was tapped and this was firing. So it already takes the detection of the gestures out of your responsibility and will just tell you, okay, I've detected this gesture. And there are a lot of different basic gestures that are already in there. So for example, detecting pinching, which will also give you a scaling amount that you know how much the pinch gesture has been performed. For the rotation, what sort of rotation happened, whether there was a swipe, whether it was a panning around, or for more specific gestures like panning in from the side of the device. So for example, in many of the basic apps, if you use the Notes app, for example, panning in from the side will go back to the previous screen, and you can also use that gesture recognizer to detect that. And you don't necessarily have to use the interface builder to add these gesture recognizers to your app. You can also do that in code, that you create a gesture recognizer and associate that with your view. So, but these are very basic gestures that are often used, and it's quite handy to have those. But if you want more complex gestures that you can react to, for example, if the user is drawing a Z or squiggly line on your screen, then you can also directly access the touches. So there are a couple of methods that UIView already hands to you. So if you override, for example, the touches began, you get all the new touches that are detected. With the touches moved, you get the location where a specific touch moved to and what get updates that way. And touches ended if that touch lifted up again. So, and you can use that to filter and apply your own processes and detect your own gestures and implement them that way. So with that, since we saw, okay, we have these view classes. Yesterday, we had in our example a view controller. It's something to keep in mind that using UIKit is very closely related to the model view controller style of programming. And you probably, or you are most likely aware of how a model view controller works. So with this, I just want to give you an overview where the specific iOS structures fit into this paradigm. So for the view category, you have the storyboard that you set up in Interface Builder, and there you define how your UI looks like. And if there's an action that the user is interacting with a button, for example, that is passed on then to the view controller, taking the controller part in model view controller. And that is done by via the IB action, for example. And the controller is then, for example, updating the model, which could be a specific model class that you just implemented, or if you use, for example, core data, that it is changing something in the persistent storage. And that would also happen then with model controllers that adapt this model so that it is all in sync. But it is something to keep in mind when using UIKit, that this is something that easily helps you to separate your classes. And with that, we've reached the end of today's lecture. We have talked in the beginning about strings and how to create functions in Swift. Talked about the difference between classes and structs, and how you can set those up. And again, the most important thing is that for classes you have your pointers, while structs are copied around. And for collections, we looked briefly at arrays and dictionaries. And there again, collections are value types. So that is something that's different from other programming language, so something to keep in mind. And next week, we'll then finally look at optionals and how to handle them and what to look out for there. The guard statement is then also something that is closely related to that. And also we look at inspection and typecasting that you can use to structure your code a little bit better. And then on the UI side and the Xcode side, we'll look at segues and navigation controllers. So different ways to show different elements, to show different screens and navigate between them. But with that, we're done for today. And if there are any questions, I will look at the chat log and answer them either next week or in the Moodle room. And with that, thanks a lot. Jan, do you have anything left that I missed?
No, I think that was great, and I think there weren't any questions that we couldn't resolve in the second part of the class there.
Perfect.
I do have one thing though. I think everybody should be aware that even if you don't have like explicitly spelled out assignments, we are assuming, of course, that what we're doing here is not just you getting flooded with information about Swift and UI code in Xcode, and then you leave it at that, right? So you should really use the time in this week and next week to try out these things, play with Swift, write some code. Even if you don't write iOS apps, build some simple command line apps, try these features of the language, because use the Swift playgrounds. They're a great resource. They will immediately point out the mistakes you make, and there are so many small things that are going to catch you when you pick up a new language. I just want to make sure that by the time we are done with this, because we're doing this fast, right? And by the time you get into the advanced topics in just a few weeks, you have a reasonable understanding of Swift and the basics of UIKit, so that you can actually dive into these APIs. Otherwise, it will just look like Chinese to you, unless you are Chinese and you can read that. So make sure that you familiarize yourself with the language and the way code looks and the patterns people use to code. We've recommended the 2 textbooks to you. Those will take you through this at a very relaxed pace. They're an easy read, but they take the time to read because they're very flowery, I would say, maybe, or verbose and everything, very small steps. You can take a look at the Swift Programming Language Guide. That's also a good document to get started. That is a little faster in providing things, and you'll find it. I think this is swift.org gets you there. So there's a bunch of resources out there, but code, write stuff, have the compiler yell at you, have the syntax checker yell at you, use autocomplete, fail to use autocomplete, understand why it's failing, do all these things now before, and because we're not going to slow down, right? We need you to be picking this up as we go. So this is not just us telling you about Swift. This is you learning Swift, and you only learn by coding.
If there are other pressing questions also from an administrative point of view, just drop me a mail and I'll get to that. All right, and then that's it for today. Thanks a lot for joining, and see you on Monday.
This content was provided by RWTH Aachen University.